How many leaves on 14 clovers? Here's a picture of one clover. 3 times 14. If I have 14 of these little guys, right, then I have 14 times 3 leaves. That makes sense to us, right? But then when we go to say, well, how many atoms in 14 molecules of water, we go, wah! How could we write this out and show it? And you're like, why would I want to do that? Well, 14 clovers, and I want to know how many leaves. Because I know how many leaves are on one clover, oops, not the number yet, I can write it out like this. So 14 clovers, there are 3 leaves on one clover. What is that? 42. The answer to life, the universe, and everything. 42 leaves. Would that be exact? Yeah. Because you can count exactly 14 clovers. And we're not talking about damaged clovers. We're talking about perfect clovers. Every one has exactly 3 leaves. Okay? So then it's exactly 42 leaves on 14 clovers. Any questions, comments on that? Does that make sense? Yeah. Well, that's why we're doing it, because this one makes sense. We could do that with legs on spiders. Ew, right? Each spider has 8 legs. So if I had 2 spiders, how many legs? 2 times 8, 16. Chairs have 4 legs. My mom always used to ask me that when I was tipping back on my chair at the dinner table. How many legs does a chair have? And that meant I was supposed to sit down because I was only on 2 of the 4 legs. But chairs do have 4 legs. And then here's a water molecule. There are 2 hydrogen atoms in one water molecule. So just like we look at the chair, we see, well, there's 1, 2, 3, 4 legs. This is a water molecule. The hydrogens are the white ones, 1, 2. We look at the formula. There's 2 hydrogens. So we have these sorts of relationships, conversion factors, in the chemical formula. Everybody okay with that? Looking at those relationships that are part of the chemical formula lets us convert between moles of a compound and moles of one of the elements, or vice versa. So 1 mole of carbon tetrachloride, this is what it looks like, contains 4 moles of chlorine atoms. If I had a dozen of these, I'd have 4 dozen of those. If I have 1 mole, I have 4 moles. So if I want to know how much chlorine is in an amount of this is the relationship I need to use. Find the number of moles of oxygen in 18 moles of carbon dioxide. So I've got 18 moles of CO2, and I want to go and find out how many moles of O. So I'm going to have moles of oxygen on top and moles of CO2 on the bottom. Here, it's important to say moles of what? If we're talking about dozens of spiders and dozens of spider legs, just saying a dozen isn't going to help because we were talking about 2 different things. So here I need to say mole of what? Mole of oxygen, mole of carbon dioxide. So mole of carbon dioxide cancels mole of carbon dioxide. What's the relationship between oxygen and CO2? 2 to 3 is a good guess. In this formula, so if I have 1 of these, how many oxygens? 2. So in 1 unit, I have 2 atoms of oxygen. That means if I have a mole of CO2, I have 2 moles of oxygen. Okay? So there's 2 moles of oxygen and 1 mole of CO2. So then there are 36 moles of oxygen in 18 moles of CO2. Questions? Because if I had 18 bicycles, and how many wheels would I have? 36, because each bicycle has 2 wheels. If I had 18 dozen bicycles, how many dozen wheels would I have? 36 dozen. Okay, so mole and dozen work the same way. Question?
How do you figure out moles when the numbers don't convert so easily?
Well, these numbers in here are always going to be beautiful whole numbers. This number could be any ugly old thing, and we'll see some of those in a minute. Here's one it's not necessarily ugly number, but it's not as round and whole. 1.4 moles of sulfuric acid, how many moles of oxygen? 1.4 moles of H2SO4, and we want to find moles of oxygen. So we put moles of oxygen here and moles of H2SO4 down there.
4 to 1?
Yes, 4 to 1. When we look at this formula, H2SO4, in 1 unit, there are 4 oxygens. In 1 mole, there are 4 moles of oxygen, 4 to 1. Don't overthink this part. We're just looking at the formula and seeing how many of those are in one of them, one of the units.
So when will it get more complicated? Like, will it get coming?
It's coming. When will it get more complicated? It's coming. I don't know exactly when. It could be on the next slide. I just don't remember.
I have a question.
Uh-huh.
So we just ignore that too?
This too?
Yeah.
We don't need to do anything with the 2. The 2 is referring to how many hydrogens there are.
Mm-hmm.
So if we were supposed to find the moles of hydrogen, we would need the 2. But we're just looking at the oxygens. So if we're figuring out how many wheels on a bicycle, I really don't care how many seats there are.
To determine the number of moles of one atom, can you just, like within that compound, can you just see how many atoms there are? Like the subscript?
Yeah, it's the subscript. And so the ratio, here we have 1 molecule, stupid long word. 1 molecule is equal to 4 atoms of oxygen. Okay, each molecule has 4 atoms of oxygen in it. And then what I'm doing is I'm just multiplying both sides by the same number, by Avogadro's number, and I get 1 mole of H2SO4 is 4 moles of oxygen. Okay? So this is going back to our initial question about sodium and sodium chloride. What mass of sodium chloride contains 2.4 grams of sodium? This formula gives the relationship between moles of sodium and moles of chlorine and moles of sodium chloride. It does not give us any relationships about grams. So what we're going to find is that moles are going to be in the middle of most of our calculations. There's a TV show called Malcolm in the Middle. So the chemistry version would be moles in the middle. If you're not sure what to do, try putting moles in the middle, and it'll probably help. I can't remember if I was supposed to, oh yeah, I guess I'm supposed to calculate that here. Okay, so mass of sodium chloride, 2.4 grams of sodium. So 2.4 grams of sodium, and we want to know how many grams of sodium chloride. We don't know the relationship between grams of sodium and grams of sodium chloride. But we know the relationship between moles of sodium chloride and moles of sodium, right? If we look at the formula, there's one atom or ion of sodium in 1 unit. So that means that there's 1 mole of sodium in 1 mole of sodium chloride. Just looking at the subscripts, the unwritten subscripts in the formula. So we're going to have moles in the middle. So I can convert grams of sodium to moles of sodium, because the molar mass of sodium is right there on the periodic table. This relationship, coming from the formula, I can go from moles of sodium to moles of sodium chloride. And then using the molar mass of sodium chloride, I can get the mass of sodium chloride. Now, it may seem like there's a lot of steps here. Once you become familiar with the steps, you can do the steps very quickly, and all you need is a periodic table. Could it be done shorter? Well, yeah, but then you'd have all these other factors that you'd have to remember, and it's not worth it. So that's what we're going to do. So now, this is where dimensional analysis is really going to start paying off for you. So I've got this path, grams of sodium to moles of sodium to moles of sodium chloride to grams of sodium chloride. It's really important to have that in place. 3 arrows, 3 conversion factors. We're doing the same thing, just with some kind of weird looking units. So grams of sodium to moles of sodium. Next is moles of sodium chloride. And last is grams of sodium chloride. I'm just putting the units in. So grams of sodium, and that cancels. Moles of sodium, and that cancels. Moles of sodium chloride, and that cancels. I have to go to moles because mole is a counting number and relates numbers of particles. The chemical formula tells me there's 1 sodium ion for every chloride ion. There's 1 sodium in 1 unit of sodium chloride. It's only in terms of numbers of atoms and ions. It doesn't translate to masses because all of the atoms are different masses. So any questions about the units here? You okay with it? Kinda? Maybe? Well, nobody's saying they're not okay with it. Grams to moles, molar mass. The numbers come from the periodic table. If it's an element, you just pull it off and write it down. What's the number under the symbol for sodium?
22.99.
Yeah, if you round it to 4 sig figs, it's 22.99. 1 mole of sodium weighs 22.99 grams. Over here at the end, we've got a compound, and so we're going to have to calculate that. There's 1 sodium, 22.99, and 1 chlorine, 35.45. And some days I remember that, and other days I don't. Yeah, 58.44. So that means 58.44 grams of sodium chloride is the mass of 1 mole of sodium chloride. 58.44 grams is 1 mole. I don't have to think about where to put the number. The unit, I put it with the unit that it had over here, and so that just tells me where to plug it in. This ratio I get from the formula. I wrote it out here. There's 1 mole of sodium in every mole of sodium chloride. So there's 1 to 1. So 2.4 grams of sodium divided by 22.99 times 1 divided by 1 times 58.44. 2 sig figs. 6.100 grams. 6.1 grams of sodium chloride. You could eat 6.1 grams of sodium chloride in a day, provided you didn't get in sodium from anything else. That's an awful lot of sodium chloride. We can't just look at the formula and predict how much sodium is in there, because they don't weigh the same amount. If they had the same mass, then it would be half, right? But they don't have the same mass, and so we need to do a calculation. Any questions? Mm-hmm.
One mole of sodium and 1 mole of sodium chloride.
Mm-hmm.
You just know that difference.
I get this from looking at the formula. So in this 1 unit, how many sodiums are there? 1. So there's 1 sodium in 1 NaCl, 1 mole of sodium in 1 mole of that.
So there was chlorine, it would be 1.
Yeah, for chlorine it'd be 1 to 1. If I'm looking at H2O and I'm looking for hydrogen, it'd be 2 moles of hydrogen to 1 mole of H2O. Okay? Sometimes it's the simplest ones that we're like, what? How did that come about? No, it's just really, we're just looking at this. Oh, there was another example. Okay, find the mass of oxygen in a 5.8 gram sample of sodium hydrogen carbonate. Here's the formula. So 5.8 grams of sodium hydrogen carbonate, NaHCO3. And I want grams of oxygen. What unit do I probably need in the middle? Moles. I need moles in the middle. I can go from grams of sodium hydrogen carbonate to moles of sodium hydrogen carbonate. That's the molar mass. We have to calculate it. It might be tedious, but we can do it. And the formula is going to give me the relationship between moles of the compound and moles of oxygen in the compound. And then I can go from moles of oxygen to grams of oxygen using the molar mass of oxygen. Okay? Once you've got the path, you just follow the pattern of dimensional analysis. So 5.8 grams of NaHCO3 times and a line, times and a line, times and a line. Copy down the units. Moles NaHCO3, and yes, you have to write all the stupid chemical formulas. Same units. You see that? Previous unit comes into the denominator because I want those to cancel out. Don't scribble them out. You still want to be able to read them, but just cross them off. You can do these, put the numbers in whatever order you want. I like to do the easy one first. Right now, this one seems easy to me. The molar mass of oxygen is just on the periodic table. 1 mole of oxygen weighs 16.00 grams. That one looks yucky. I don't want to calculate that one yet, so I'm going to look at this. It's kind of sloppy. When I look at this formula, I'll look at this one because it's neat. I look at the formula, there's 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens in one formula. So there's 3 moles of oxygen per 1 mole of the whole compound. 3 moles of oxygen to 1 mole of the compound. And then I do have to calculate the molar mass of sodium hydrogen carbonate. So sodium and hydrogen and carbon and 3 oxygens. .008 grams equals 1 mole of sodium hydrogen carbonate. That's baking soda, by the way. Now, is the 8 really a significant figure? Probably not, but this only has 2 sig figs, so does it matter? No, it's simpler to just write it all down. 84.008. So 5.8 divided by 84.008 times 3 times 16. I should have 2 sig figs. 3.3 grams of oxygen. So there's 3.3 grams of oxygen in 5.8 grams of baking soda. I know you were dying to find that out, right? Burning question. Yes?
My calculator got 3.2, would that still be?
Your calculator got 3.2. Well, let me check my math. It's always a good idea to type it through twice. And if you have a calculator that allows you to look at what you typed in, that can be helpful. I still get 3.3. So unless you're using a significantly different molar mass, it should be 3.3. Yeah.
So the second step and the last step, the moles are always going to be 1, right?
Yes. Yeah, so we're using molar masses as conversion factors. The molar mass is the mass of 1 mole. And so this is always going to be 1 mole is how many grams? 1 mole is how many grams? The only time that the moles isn't going to be 1 is in the middle, the mole ratio, moles of something to moles of something else. That may or may not be 1, it depends. Any other questions?